Today we are going to be looking at sets. The topic set is a universal language or tool for both the sciences, the arts, and the social sciences. Sets. We look at the terminology. First of all, let's define what a set is. So by definition, a set is a collection of well-defined objects or numbers. Objects or numbers. For example, a set of cutlery, a set of mathematical instruments, a set of integers, etc., etc. Sets are enclosed in a curly bracket. It's a special type of bracket called curly bracket, and this is a curly bracket. Capital letters are used to represent a set, and the elements or members of a set with lowercase, that's small letters. The lowercase letters are small letters. And these are separated by a comma. So for example, a set A is equal to the elements A, E, I, O, U. Each of the elements are separated by a comma, each of the letters. You will recognize this as the vowels. Another example is a set B is equal to 2, 4, 6, 8. Maybe we can define this as the first 4 even numbers. So these are examples of a set. No other bracket is allowed. For example, a square bracket is not allowed. The ordinary bracket is not allowed. Or whatever design you want to have is not also allowed. These brackets are not allowed in the language of sets. Only the curly bracket are allowed. Take note of that. In discussing a set, we also look at member or element of a set. When you talk about the member or element of a set, mathematically it is represented by a symbol. So the symbol here, the symbol that looks like E here, and this symbol here with a slash on that same symbol E, represent member of or element of, and not a member of or element of respectively. So the first one is member of or element of. The second one is not a member of or element of. Thus, if you have E in the first set we wrote, where we said A is a set equal to the vowels, E is a member of the set A, because E is a vowel and is in the set A. 4 is a member of the elements in set B, where we have set B as 2, 4, 6, and 8. And then we also now see that D is not a member of the set A. Obviously, D is not a vowel and is not even A among the set A elements. 5 is not also a member of set B. 5 is not even, and it is not also in the elements of the set B. Since sets also involve elements or numbers or objects, it means that they can be countable and sometimes they can be uncountable. In other words, we have what we call the finite set and the infinite set. So we have the finite set and the infinite set. For a finite set or a finite set contains countable elements, while the infinite set has uncountable elements. Take that again. For the finite set, we have the elements that are countable. They can be 2, they can be 1, they can be 20, they can be 100. They are countable. But for the infinite set, they are uncountable. And these are represented as follows. For example, a set A is equal to, the elements are 2, 4, 6, 8, 10. you discover that we have 1, 2, 3, 4, 5 elements. They are countable. Such a set is called a finite set. While a set B has ellipses, these 3 dots in mathematics are called ellipses. So we have dot, 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 2, 4, 6, 8, 10. It means that this set of number continues to your left, unending. Or we can write it as 2, 4, 6, 8, 10, and then we have the ellipses at this back of it. It continues in that order. Or we can have ellipses at the beginning, have the elements, and have ellipses at the end. They are all infinite sets. And this is how they are represented. Take note of how the finite sets are represented and how the infinite sets are also represented. Now let us look at the number of elements in a set. The number of elements in a finite set S is denoted NS. Now let's take for example a set S equal to 1, 3, 5, 7, 9, 11, 13. What then is the number of elements in this set, NS? We will count the number of elements 1, 2, 3, 4, 5, 6, 7. So the number of elements NS is equal to 7. So this is the number of elements in this set S. The null or empty set. The null or empty set is a set that contains no element, and this is represented by the symbol phi or the curly brackets without any entry in between the curly brackets. The singleton set is another set with only one element. It is also called the unit set. It means that it contains just one element. For example, you can have a set A is equal to, and then you have an element here, and that is it. It contains just one element, and this is called a singleton set. Universal or entire set. This is the set containing all the elements under consideration, and is denoted this symbol U or this symbol for entire set. Both are used interchangeably. If we are talking about a set of students in a school, any student in that school qualifies to be among that set. So the entire school becomes the universal set. But if we are looking for a student in SS1, in senior secondary 1, then we do not need to bother to go and look for students in GSS1 or the basic school 1 or SS3. All we need to focus is SS1 students in that school. Therefore, SS1 students become the universal set. So that is why we say that the universal set is a set that contains the members or elements under consideration. We have again the disjoint set. We say that two or more sets are disjoint if they have no element in common. For example, we have a set A equal to 2, 3, 5. And we have a set B is equal to 1, 4, 6, 7. Then we discover that a set A and B have no elements in common. When the set have no elements in common, we say they are disjoint. In other words, the intersection. So we say A intersection B is equal to empty set. We can write it like this, or we write it like this. We have already seen what this means, empty set. So there is no common element between A and B. So we write A intersection B is equal to empty set. Subset of a set. A subset of a set is a set containing some of the elements of the set. Now let's take for example a set A, and this is defined as 1, 3, 5, 7, and 9. And another set B, and this is defined as 3, 7, and maybe 9. Then we say that B is a subset of A. A subset. Sometimes we put this line here, a proper subset of A, meaning that all the elements in B are found in A. In another way, we can write that A is a superset of B. A superset of B, meaning that B is contained in A. B is contained in A. B is contained in A. All the elements in B are in A. We can also write it in this form. This is a superset. This is called superset. A is a superset of B. B is a proper subset of A. So here we can have proper subset of A. We look at sets of value. In sets of value, we use the inequality symbols to represent the sets. So this is defined using inequality symbols. Now let's take for example, we have a set A, and this is defined as S such that S is less than 0, and of course there's a comma. Our S belongs to the set of Z. Z here means integer, and then this column means such that. So we read this as A is a set S such that S is less than 0, and S is a member of Z, where Z is an integer. We have now used the symbol less than to define the set A, and we may be asked to list the elements of this set. So our A, therefore, by listing the elements, we start from, remember we have many numbers. Let's say less than 0, being an integer, we have the next one be minus 1, and then we have minus 2, and then we have minus 3, and then we have ellipsis, ellipsis, ellipsis. And we can close it like this, meaning that it's an infinite set. This set is an infinite set. It continues ad infinitum. It has no end. It's not countable. So we have actually represented the set A using the inequality symbol, and we have now also listed the elements of that, and we have found out that this is an infinite set. It's an infinite set. Another example could be a set B, and set B is defined as S such that our 0 is less than S and S is less than 5, where S belongs to the set of natural numbers. Now let's look at what we have said. This stroke here means the same thing as such that, and whereas this one here is a set of counting numbers, the natural numbers. Natural numbers. And the natural numbers here, we are talking about 1, 2, 3, and it goes on like that. Now, we have now defined a set B. If we are to list the members of set B, the members of set B are between 0 and 5. Between 0 and 5. No fraction is needed because we are talking about natural numbers. So between 0 and 5, you have 1, you have 2, you have 3, and you have 4. And this is the set B, by listing the members of that set defined by the set builder notation. Equal sets. If every element of the set A is also an element of the set B, then A is equal to B. Let's say, for example, here is the set A, and is defined by the elements 1, 3, 5, 7. And then we have another set B, and it's defined by 1, 3, 1, 3, 5, 7, and 7. Then we say that A is equal to B. The reason is because 1 is repeated here, 3 is repeated, and 7 is repeated. But the digits remain the same. So we have here the set A equal to the set B, not minding the repetition of some of the digits. Digit 1 repeated, digit 3 repeated, and digit 7 repeated. Now we take a look at power set. The power set is the set of all the subsets of a set. And this is denoted by PA, and where our A is the set. Let's take, for example, we have a set A, and it's equal to the element 1, 3, and 5. And for us to write the subset of A, so our PA will be equal to, we have the set 1 is a subset of A, 3 is a subset of A, then we have 5 is also a subset. Let's combine now. 1, 3 is a subset, 1, 5 is a subset, and then of course we have 3, 5 is a subset. Then we also have, in this case, we have gotten how many now? 1, 2, 3, 4, 5, 6. Then we also have that our 1, 3, and 5 is a subset. And then finally, the empty set is a subset. So we close the bracket, that is the curly bracket, enclosing all the subsets of the set A. So these are the power sets of the set A. You now discover that we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 subsets of the set A containing 3 elements. I want you to take note of something here. The empty set is a subset of every set, and a set is a subset of a set, as you can see in the example above which I gave to you. You discover that 1, 3, and 5 was a subset of that set, and then of course the empty set is also a subset of that set. The number of subsets in a set. We say that the number of subsets in a set is denoted by 2 raised to power n, where n is the number of elements in the set. And let me give you an example of what we are saying. Here is the set A, and it contains the elements 0, 2, and 4. And I ask you, find the number of elements in the set A. So the number of elements in A will be equal to 2 raised to power n, and that means 2. Our n is the number of elements there, and they are 1, 2, 3, 2 raised to power 3, and that will be equal to A. So sometimes the question simply asks you, find the number of subsets in a given set, without asking you to list the subset of a given set. This one directly, you apply the formula 2 raised to power n to get the number of subsets that can be derived from a given set A. In this case, we have only 3. So if you have a situation where you have 4 elements, so let's say 4 elements, the number of subsets will be 2 raised to power 4, and that is equal to 16, and so on and so forth. So with this, you can find the number of subsets in a given set. Complement of a set. The complement of a set is the set of all the elements in the universal set which are not in the set. Now, what am I saying? Let's say, for example, a set defined as 1, 2, 3, dot, dot, maybe 9 and 10. The counting numbers from 1 to 10. And then let's define a set A to be equal to 1, 3, 5, 7, and 9. Now we write that the complement of a set is, so A complement will be equal to the elements that are in the universal set which are not there in the set A. And what are those elements that are in the universal set? 2 is there, 4 is there, 6 is there, 8 is there, and 10 is there. So therefore we write A complement is equal to 2, 4, 6, 8, 10. Notice the superscript C that I've written here, or the power C that I've written there. Or we can write A prime also at the power level to be equal to 2, 4, 6, 8, and 10. Observe here now that we can use A complement the way I've written it here, or we say A prime the way I've written it here. Both of them are synonymous, they are the same, referring to the complement of a set. Intersection of a set. This is represented by the symbol N. Look at this symbol here. It looks like N, but not actually N, but this is how it is written. So we say that the intersection of two or more sets is a set containing the elements common to all the sets. Let's take for example, we have the set A, and this one is defined as the elements are 1, 2, 3, and 5, and we have another set B, and this is containing 2, 4, 5, 7, and 9. Then we talk about A intersection B will be equal to the elements that are common to both sets are 2 is there and then 5 is also there. These are the two elements that are common. So symbolically we will write this as A intersection B is equal to the set S such that your S will belong to the set A and your S will belong to the set B. This is a symbolic representation of A intersection B. We have union of a set represented by U. Union of a set. Now the union of two or more sets is a set of all the elements belonging to the set without repetition. In other words, we will take all the elements in the two sets or in the three sets without repeating them, and that will form the union of those sets. Let's take an example of this. So our example is if a set A is defined as 1, 2, 3, and 5, and then another set B is defined as 2, 4, 5, 7, and 9. Our interest is to find A union B will be equal to 1 is there, 2 is there, and it's also here, 3 is there, 4 is there, we have 5, we have 7, we have 9. We have the 2 here and the 2 here. We also have the 5 here and the 5 here. So we take only 1 without repeating them. So this becomes the union of the set A and B. Symbolically, we are saying that A union B is equal to the set S such that S belongs to A, or our S belongs to B, or our S belongs to both set A and B. So this is a symbolic description of a set A union set B. Elements in set A and elements in set B, or elements in set A and B. That gives you the definition of the union of two sets. Another interesting term is set difference. Set difference. Written A minus B, where A and B are two different sets. Now this is the set of all the elements belonging to A but not to B. It is called A difference B and denoted A minus B. By this, it implies that take all the elements in B away from the elements in A. What remains in A is the set difference. For example, our A minus B, that is A difference B, will be equal to a set S, so that S will belong to A, but S does not belong to B. So there's the elements in A, but those elements are not in B. Alternatively, B difference A means the elements that are in B, but they are not in A. We can take a look at an example of what we are saying. Assuming we are given a set A to be equal to the following elements. We have 1, we have 2, we have 3, we have 5. And we have another set B having the following element. We have 2, we have 4, 5, 7, and 9. Good. So our A difference B will be equal to, what are the elements that are in A that are not in B? 1 is in A, you can see that. 2 is in A and 2 is in B. 3 is in A, and then 5 is in A and 5 is also in B. Even though 7, 9, 4 are in B, but the elements that are in A that are not in B is our interest. So they are 1, 3. These are the two elements that are in A which are not in B. Similarly, our B difference A will be equal to, we look at the elements in B. 4 is in B and is not in A. 7 is in B and is not in A. 9 is in B and is not in A. And of course we have 4, 7, 9 are the elements that are in B, but they are not found in A. So B difference A gives you 4, 7, and 9. And A difference B gives you 1 and 3. I hope you understand this very well so that you'll be able to apply it in solving problems. Now let's look at Venn diagrams. Sets can be represented in circular or closed curves such as this. This one, you can see the rectangular shape which encloses what we call the universal set U, and then we have set A, the circular set A, and the circular set B. So a set can be described in this Venn diagram in this way, where this region here is the region where which we call the intersection of A and B, and the elements in A only will be found here, elements in B only will be found here, elements outside A union B will be outside the two circles but within the enclosed rectangular box. The same thing goes, we can have a Venn diagram represented as this, where you have three sets. In this case, there is nothing common between the set A and the set C, but set A has something common with set B, found in this region. Set B has something common with set C, found in this region. But there is nothing common between set A and set C. So set A and C are said to be disjoint. The third one is this one, and this one is represented by the same three sets, A, B, C. In this case, there is something common between A, B, and C. So there is an intersection between A, B, and C, which will be found in this region. So these are three formats of representing a Venn diagram involving either two sets or three sets. Here are some representation using a Venn diagram. The first one here, figure 1, we have the universal set, and then we have the set A. and then around the set A is shaded, and that is A complement. So we have that the set A and the outside is A complement. As a matter of fact, you now discover that our A union A complement is equal to universal set. The second case, we have the universal set. We have two sets here, set A and set B. Set A is included in B, is inside B. So here, A is a subset of B. Now, from this place, you can draw out that our A intersection B is equal to A, as you can see. And while our A union B will be equal to B. We will now also consider a third case. Here we have a universal set involving two sets, A and set B. The point of intersection is recorded here as B and is shaded. While this portion is A and this portion is C, outside the two circles or the two sets is D. Specifically, we have highlighted the portion here with the dotted point as A intersection B. That is the portion represented by B. Now from here, we can also deduce that our A plus B plus C is equal to A union B. The union of the set A and B is the sum of the elements in A and the elements in B plus the elements in C. While B on its own specifically is defined as A intersection B. A on its own is defined as A union B complement outside B. And C similarly is A complement union B, while D is A union B complement, which is also equal to A complement intersection B complement. This is De Morgan's law. This one is De Morgan's law. Okay, from there we look at the fourth case. And the fourth case here is represented by this diagram here. We have two sets, and we have the set A that is inside or included in set B, and we have the outside shaded. This A region is S, while the other region is Y. What we are trying to point out in this case is the difference of U and A. So U difference A, remember when we talk about the difference of two sets, so U difference A means that all the elements that are in U which are not in A, and the elements that are in U that are not in A are found in the location of S and the location of Y, which gives you the element S plus Y. That is A complement, which is the shaded portion. That gives you the difference of U and A. Now let's look at a situation where we have three sets intersecting at the point S. We have the set A, B, and C. We have the regions represented here by letters A, B, C, S, D, E, and F, and outside the three circles or three sets is D, elements outside the three circles. We want to look at each of the compartments and define them in terms of set notation. So in this case, we have the first one, number one, the S, which is the point where all the sets have common elements. And this is represented set-wise as A intersection B intersection C. Now let's take the second case. Assuming we are looking for the elements in A union B union C, it means we are interested in all the elements in A plus the elements in B plus the elements in C, plus the elements in D, elements in E, and then plus the element in F, and finally the element AS, which is common to the three sets. That gives you A union B union C. Now let's look at the compartment A on its own. This one will be defined by A, the small letter A is in the set A, so A is there, intersection B is not there, and then intersection C is not there, which also can be written as A intersection B union C and complement. So this represents the compartment A as far as this case is concerned. We look at the compartment B. B here involves the intersection of A and B. So we have A, intersection B, then intersection, the complement of C, because it's outside C. So this now represents the portion lettered B in this case. We can as well look at even the portion lettered C along the line. If you look at this, C is involving set A and set C, but no B. So we can write as A intersection C, then intersection B complement. Now let's look at the location, the portion D. D here involves B and C, but no A. So we can write this as A complement intersection B and then intersection C, as far as that case is concerned. So that defines set-wise that portion lettered D. Then we can go on and look at another portion, let's say lettered E. If you look at E, in this case, there is no A and there is no C. So we actually have B intersection A complement intersection C complement. Now these two can be written as, after our B, intersection A union C or complement. They are both synonymous. Take note of that from De Morgan's law. We can even have the third case. Let's consider the third case here, and this one is F. Our F will be equal to, F is involving only C. There is no A, there is no B. So we have A complement intersection B complement intersection C. And again, this portion can be written as A union B or complement then intersection C. That has also defined that location. We look at location G, which is outside the three sets. And this one is represented, that is totally outside. It means A complement intersection B complement intersection C complement, or A union B union C or complement. That represents the location G, which is outside the three sets I described above. We can also have the other location here, this time around. For example, the location B plus S plus C. B plus S plus C involves A, but it also involves A, B, and C. The intersection of A, B, and C. So this location, we can have it as A intersection B. As you can see, A intersection B gives you B and S, and of course, union C and S is the intersection of A and C. Union A intersection C. This one will give you the definition or the description of B plus S and then plus C. And of course, you can see now that if you write this one, this is the same thing as writing our A intersection, open the bracket, B union C, which means intersection distributes over the set B and set C. So distributive law. Let's look at another case where you have A plus B plus C plus S, that's all the elements in set A, and then plus the D elements that are in B and C. This is equal to the elements in A, because all A, B, C, and S are all in A, then the union of the elements in B intersection C. So the union of the elements in B intersection C. That will give you the definition of those locations A, B, C, S, and D. Algebra of sets. Let us look at the algebraic format for calculating problems on sets. Now, if NA represents the number of elements in a set A, Then 1. The number of elements in A union B will be equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. The reason for this is because when you add all the elements in A and you add all the elements in B, their intersection you have added twice. So you need to remove one of it in order for you to get the number of elements in A union B. The second case, if our intersection A and B is an empty set, which means these two sets are disjoint, they have nothing in common, then the number of elements in A union B will be equal to the number of elements in A plus the number of elements in B. Since there is no intersection, you add the elements that are in both A and B. This condition can be extended to a situation where you have three sets, set A, B, and C. And so, in the third case, we are looking for the number of elements in A union B union C, which will now be equal to, algebraically, NA, which is number of elements in A, the numbers of elements in B, plus the number of elements in C. Then subtract the number of elements in A intersection B, subtract the number of elements in A intersection C, and also subtract the number of elements in B intersection C. Then add the number of elements in A intersection B intersection C. This gives you the number of elements in A union B union C. Let's take the first example. Number 1. If S is equal to prime factors of 44 and Y equal to prime factors of 60, find Roman figure 1, S union Y. Roman figure 2, S intersection Y. Our solution, first of all, we write out the prime factors. So our S is equal to the prime factors of 44, we start with 2. And then what again we divide that? 11 is one of the prime factors, and these are the only two prime factors of 44. Then we have our Y, which will be equal to, our Y will be equal to the prime factors of 60. 2 is a prime factor of 60. 3 is a prime factor of 60. 5 is also a prime factor of 60. Is there any other number that is a prime factor of 60? No, and that is that. So the question now is 1. Find S union Y, and that will be equal to our 2, our 3, our 5, and then 11. The second one is asking you to find S intersection Y, and that will be equal to the intersection here is a singleton set which contains the element 2. So the answer to this problem is 2, 3, 5, 11, and then the singleton set 2. Example number 2. If the universal set U is equal to 1, 2, dot, dot, dot to 6, this means what? Ellipsis. This means it continues in that order. And the set P is defined as 3, 4, and 5, and Q is defined as 2, 4, and 6, and R is defined as 1, 2, 3, and 4. List the elements of the set P union Q complement intersection R. Your solution. First and foremost, you have to find your P union Q. And from the elements given to you or the set given to you, your P union Q is 2, followed by 3, 4, 5, and 6. Therefore, you can find P union Q complement will be equal to, from the universal set, you have only one that is not in P union Q. So we have our 1 intersection R. Now, your arrow contains 1, 2, 3, 4, and of course, the answer now becomes 1. And so that is the solution to the problem. Example number 3. If P is equal to 1, the set 1, 2, U, V, W, X, and Q is equal to 2, 3, U, W, 5, 6, Y, and R equal to 2, 3, 4, B, X, Y. determine P, the difference between P and Q intersection R. Difference P and Q intersection R. Our solution, we have our P here, which is equal to 1, 2, U, V, W, and S. Then we have our Q here. We have 2, 3, U, W, 5, 6, and Y. Now we're looking at P, difference Q. That's all the elements that are in Q. Here, take them away from the elements in P. So we have 2 here and 2 there, we take it away. We have U here and U there, we take it away. W and W. And then what again do we have? That is all. So we have this to be equal to 1, V, and X. So we now bring in our R. Our R is equal to 2, 3, 4, V, S, and Y. Now let's get the intersection of P minus Q. Intersection R will be equal to, let's look at the intersection. We have V here and we have V here. S is there and S is there. There is no other element that is common to both, so our answer will be V and then comma S. And that is the solution to the problem. Example number 4. In a science class of 42 students, each student offers at least one of mathematics and physics. If 22 students offer physics and 28 students offer mathematics, find how many students offer physics only. Our solution, we have here that let M be equal to mathematics and let P be equal to physics. Now we have the number that offers mathematics, you know, P, should be equal to the number that offers mathematics plus the number that offers physics minus the number that offers mathematics intersection physics. Now from the question given to us, it's a science class of 42 students. So this will give us 42 students. And then each student offers at least one of the mathematics. So all the students are offering math, physics, or both. Okay. Now if 22 students offer physics and 28 students offer mathematics, so mathematics they are 28 and physics they are 22. And then of course minus the number that are offering mathematics intersection P. Now find how many students offer physics only. So let's first of all get how many students are offering both mathematics and physics. In this way, we have here bringing minus n intersection P to the left hand side. We have n intersection P is equal to, adding this you have 50. Then taking this to this side becomes minus 42, and the result is equal to 8. So the number that offers both mathematics and physics are equal to 8. Therefore, physics only will be equal to your physics intersection, what we call mathematics complement. So no mathematician is there as far as this case is concerned. Nobody that is offering both maths and physics should be there. So only those who are offering physics, hence the algebra is of this format. Now, how many people are offering physics? We are told 22 students offer physics. So 22, take away the number that are offering both physics and mathematics, and eventually this will give you, if you take away 8 from 22, you have 14. So 14 students offers physics only. Now, alternatively, we can use the Venn diagram. So let's say using the Venn diagram, let's take this as, we have this as the universal set, and the number is 42. Then thereafter you have for mathematics, and they are 28. We have for physics, and they are 22. Now let's call the intersection S, meaning that those who are offering both maths and physics, what remain here will be 28 minus S, what remain here is 22 minus S. Since all of them are offering either physics or mathematics or both, there is no one outside the region. So we have now that 28 minus S plus S and 22 minus S will be equal to 42. Minus S plus S will go, and we have now 50 minus S is equal to 42. And so our S is equal to 50 minus 42, and that is equal to 8. So therefore, your physics only is the portion with 22 minus S, and that's equal to 22 minus 8, and the result is equal to 14. So you can also use the Venn diagram to solve that same problem.